I'm glad you said that before the video started. This is number 2, radioactive decay review number 2. Behrad, you said what this was. Tell me again.
1984. I don't know what it was though.
So 84. So that becomes polonium.
Do you use the bottom number to find out what it was?
Yes. The number of protons is what defines the element, right? It's the only thing that defines the element is the proton number. So this would decay into something different. And then of course we would have the helium nucleus along with that, and that would fly off at high energy. Okay. There's a periodic table at the back of the textbook. Right there, very back page. Yeah, there's a periodic table in your data book. Is there? There's a list of elements for sure. Because you'll need the masses and stuff, which I'll show you. Okay, let's say you find a rock. I don't have a rock in here, I don't think. The penguin? This is a rock, and we take a Geiger counter. I'm going to pretend this is a Geiger counter. And you put it close to it. What will you hear?
What's a Geiger?
Oh. Have I not shown you the real Geiger?
Is the sound thing?
Yeah, the sound thing. Okay, so let's just draw it. I'll show it to you in a second. Let's draw it. Here's your...
No, I saw it on TikTok. Like one of those sound things.
Also same.
Let's say you got a rock.
I don't know. It's like it measures like.
And you get your...
Should we draw this?
Yeah. Ours looks kind of like this. I'll dig it out for you. And it has a little dial in the front, and there's a cord, and it goes out to this kind of tube thing, and you can hold it. And it has a little film on the end.
I need to write the rock.
And the particles coming out of the rock, if this rock is decaying, it'll have radioactive nuclei flying out and hitting that tube. The tube is filled, this is called a Geiger-Muller tube. Let's do it in blue. That's what they used to be called anyways, and now we call them Geiger counters. Muller got dropped. It's a Geiger counter. And inside this tube is a low density gas. It's an inert gas, usually like, well, it used to be argon. I don't know what they use now, but I think they do something, it's a halide gas or something. So inside this tube, and you do have to know how this works for IV.
Not for the quiz, though.
No, I won't ask you about Geiger counters for the quiz, but it could be something they could put on the IB exam. So this is a low density gas. And an anode and a cathode. So what's separating the anode and the cathode, and sometimes they're rods, sometimes they're plates, whatever, and the gas is what's separating those two. And we plug the thing in, and we put a very high potential across the cathode and anode. So like maybe 500 volts or something like that. So we provide a high potential.
Free what? What provide?
Yeah. Yeah, so you have a big EMF between there. So you plug it in and you get a big potential between the electrodes. And then what happens is when the particle goes into that gas tube, the particle hits the atoms of the gas and ionizes the gas. What does ionize mean? Yeah, it knocks an electron off. And that electron goes and hits the next atom of gas. And that atom of gas creates more electrons, which hit other atoms of gas. And you have what's called a Townsend avalanche, is what it's called. It's part of the IV curriculum. So I'll just continue this. Townsend avalanche. Occurs. I could probably say that a little bit better, but so free electrons create a current. So you got these two electrodes and you have this big voltage between them, but there's nowhere for it to go. There's no free electrons for it to move through. But then when the radioactive particle hits, you get this avalanche of free electrons, and then you get this current for a short time. And we hook that up to a speaker. And so when you get a current, you get this click. And then it goes click, 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 click. Okay. And so the Geiger counter tells us for every click is one particle decayed. Does that make sense? Townsend. Sorry, I didn't write it very clearly. This is supposed to be an N. You don't have to know the name of this, but you have to know how it works.
For the quiz?
No, for the exam.
Okay.
So, it depends. Some years it's not on there at all. And some years it's in a problem, like they kind of parse out a radioactive problem. They want to see how the clicker works. Yes, Ryan. I'll write it again.
So wait, what? They could say
That's
like,
too
oh,
messy.
there were 20 clicks. What's the induced current?
Townsend. No, they won't ask that. They'll just say, they might say like, how does one radioactive particle create a click in a Geiger counter?
That's it.
Yeah.
Just copy this then.
Yep. You just explain it. Or they might say something like, if a Geiger counter is not plugged in, why do you not hear the clicks anymore? It's because there's no potential between the electrodes, so it doesn't matter. The free electrons just float around in there and they have nowhere to go. Okay. Does that make sense? Kind of, sort of? Okay. So you have a Geiger counter, and I used to have a rock in here made of uranium, and I would put it, did I tell you this already? I used to bring out the Geiger counter and we'd hear the clicks and stuff. We can do that now too, but I'd have to find something that's radioactive. Like an old smoke detector works well.
What?
Smoke detectors use radioactive
Do
decay.
you know why smoke detectors make that noise?
Because you
you don't have batteries in them, bro. That's why.
What do you mean? What do you mean for
Well,
us?
every like 10 minutes it just goes.
For 10 minutes it goes.
No, like every 10 minutes.
Oh yeah, that's because the batteries. Yeah. I used to hold the rock up. We all did this. I shouldn't say this on video. We used to hold the rock up, and you get a student to come up in front, and you put the rock on one side of the student's head, and the Geiger counter on the other side, and you'd hear the clicks. So the radioactive particles are going through the head and into the Geiger counter. Yeah, every teacher did that. And then now they threw it away. They don't let us have it anymore. Okay, so let's talk about activity. So if you have a Geiger counter, your activity is your clicks per second, and it's also decays per second. Now, it doesn't have to be second. It could be days or weeks or months or years. But it's the decays per some time period. Or other unit. Time. A is equal to lambda n.
Well, this is lambda wavelength.
This lambda is not wavelength.
Why is there like 4 different lambdas?
Oh, there's more than that. There's a lot of p's as well. I'll write this to be clear, not wavelength. What it is, lambda is the probability of any nuclei decaying.
Where's that?
And I should say in a short time. Lambda is kind of a funny animal. You hear it defined in different ways. People will define it mathematically. It's the ln of 2 over the half-life, and we'll derive that. It's also the inverse of the mean lifetime of a particle. But I think the most intuitive way to understand it is that it's the probability of any nuclei decaying within that short time. So if you think about it, if you had 100 nuclei, and by the way, n is the number of nuclei. Let's say you had 100 nuclei, and your lambda is 1%. What's your activity?
1 click.
1 click per second. So your lambda can be in different time units as well. If your lambda was 1% per year, then what would be your activity?
A lot of seconds.
No.
A lot. Oh wait, no, not less than.
1 decay per year would be your activity, right? You have to sit there and listen for a whole year. Just click and go. It's usually much more than that because we have way more than 100 nuclei, right? And so, of course, is activity.
Is there any way to like speed it up?
Yeah, there is. Not with the same element, but different elements have much faster decays.
You wouldn't need your calories for
No, it's not that kind of a thing. It's not a chemical reaction. We talked about this, but why do nuclei decay in the first place?
Because they're too strong and weak. Okay, we review that again.
Yeah, they're slightly unstable, right? All particles have strong force pulling them in. That's why the nucleus holds together. So that's between protons and neutrons. What's pushing the nucleus apart? Electromagnetic, very good. So the protons don't like each other. They want to get away. The neutrons are holding tight. So we did an example with U-238. U-238 has a half-life of, I think it's 4 billion years. Really slow decay.
Why is it radioactive? So
It is radioactive, it's just decays slowly. U-234 has a half-life of about 70 years. It's just a little bit smaller. You want to write that down? Yeah, you should write that down.
So wait, the time it takes for uranium to decay is longer than the universe to turn around.
Well, when it depends which isotope.
No, it's 13.8 billion years.
Oh, so it's just when the universe.
It would be, yeah, it would not have decayed fully for the whole age of the universe, no. But that could be true of lots of things. So the half-life of 238, and when you see this T with the subscript half, that's half-life, right? I want to say this is 4.5 billion years. And I think this is 69 years.
How is there still uranium?
Pardon me?
How is there still uranium? Shouldn't have all of it have stickers on them.
This is not a product of that. Oh, I see what you're saying.
Like, if it,
Oh, that's a good question.
how is there still stuff?
Yeah, how is there still stuff? Why is all the uranium not gone?
New ones made, they decay.
We make new ones in the universe. Where are they made, do you think?
So,
Carlo?
Stars.
Stars.
Usually
Supernova.
Yeah.
You need a lot of energy to put big nuclei together. Anything over iron was probably made in a supernova. So you have elements in your body right now that could only have been created in an exploding star.
So basically,
You are a star,
let's
Arlo.
go.
That is correct. Love that. This is shorter because it's a smaller nucleus. It has less strong force, right? Same amount of electromagnetic repulsion because the same amount of protons, but fewer neutrons, so there's less strong force holding things together. And so it falls apart easier. Does that make sense? Kind of, sort of.
so if it was 233, would there be a way to like calculate like the ratio? If it went down.
That's getting tricky. That's getting tricky. But I can tell you how to find the half-life, which I will do right now. Okay, so let's do a little example here. I'll do this. Let's say you have a rock, and let's say it's let's say, oh, can I give you this yet? Yeah, we can do this. Let's say it's some mass. Give me a mass.
4 grams.
5? 5 kilograms? It's 5 kilogram rock. And let's say the activity that we measure is, and we would measure this with a Geiger counter. Let's say it's, I don't know, 5 clicks per second. So you'd see this, IB would write this like this. This S to the negative 1 is per seconds. And the question is, what is lambda of this material? See if you can calculate that.
What's the rock made of?
You don't need to know.
No?
No.
So how do you know
I'm
how
gonna
much?
pause this.
How do you know
Number
how
two.
much of the mass is like